just let me know. And that goes for any professor. That's a change from the old version of Blackboard to the new version. The old version was it? The old version, it was available to you as soon as you uploaded it or created something, and then we went in. If we didn't want you to see it, then we said we don't want you to see it. So, the new normal, right? Okay, let's move on. Chapter 2, review from last time. Everyone good online? Everyone can see? I can't see anybody, but okay, you guys are good. You're logged in. Cool. All right, motion, linear motion, translation, all points in the same direction. Rectilinear, then straight line. Curvilinear is some type of curved path. Angular motion, rotation on an axis. Then general motion would be a combination of the linear as well as the angular motions. A good example of this, throwing, well, I guess any type of ball. There's going to be some type of spin on that ball, and it's going to be moving possibly in a straight line, or what would maybe look like a straight line, straight direction. Basic references, standard description of human motion. Oh, we skipped the Cartesian. Wow, never mind. I don't know, my apologies. Displacement. And we went into details about why the difference between displacement and distance can be important as we moved along. So the resultant displacement, we have straight line distance from the initial to the final positions. So we had the example of baseball diamond, baseball infield, and if we hit a single, our displacement was 90 feet. So going from home plate to first base, 90 feet, point A to point B. However, if we went from home plate to second base, we would then have to use Pythagorean theorem to figure that out. It makes it easy on a baseball diamond because it is a 90-degree angle. So just simply point A to point B, first base to second base, straight over a line straight over the pitcher's mound, essentially. And there we go. Once we got that, I believe it was 127.3 feet was what the total displacement was. You can do the same thing maybe in football, soccer. Another one, how far somebody actually ran. Again, not taking into consideration the actual path that somebody was taking and going around defenders or whatever it might be. Then the distance then is the actual length of the followed path from the initial to the final position. So we're actually taking into consideration every single turn, right, left, backwards, forwards, up, down, wherever it might be. So then speed is the rate of motion taking into consideration the distance, the actual path somebody took. It's mile per hour, kilometers per hour, meters per second, feet per second. So a lot of times we're looking at the average speed over that distance. We've got the distance traveled and the change in the time, or just the total time that it took for that to take place. We can split it up into different segments, which would maybe help us get a little more detailed about maybe the instantaneous speed or velocity, if you're wanting to use velocity. In that case, you can break it up into smaller and smaller units. The smaller and smaller intervals, time intervals you get closer and closer to the instantaneous speed or instantaneous velocity, again, if you're using velocity. But the instantaneous speed then is at a specific instance in time. Now, can we actually get true instantaneous speed? That's probably when you get into theoretical physics and stuff like that. But for all intents and purposes, yes. I would imagine that even if we took a half a second or a second interval, there's very little error in the true instantaneous speed versus the average speed over that, maybe that 1 second. So, a little bit of theoretical space-time quantum mechanics for you for the morning. So if the average is not used, the instantaneous is going to be assumed. So less than or greater than the average speed, depending upon the interval that is used. Maybe some devices that are used to find this stuff. Chronographs. There's other ones that look a little bit different than this one. Someone will attach to whatever object or propulsion device that you're looking for. There are chronographs that basically on a stand, and they're light sensitive. This one here, this particular one, is actually magnetic. The bullet goes across it, and there's actually a magnet right here in the front. There's a little bit of magnet there, and there's a magnet there, and then it just measures the time that it took for the bullet to cross both of those paths, and there you go. Other ones are light sensitive, laser sensitive. Radar guns are also one that measures instantaneous speed. So, in fact, going back to that time interval instantaneous speed dilemma, there's still a time that it takes. Even maybe a bullet that's traveling at 3,000 feet a second, there's still a fraction of a fraction of a second that it's taking for it to go between those 2 points. So it's not necessarily instantaneous speed, but for our version of time, it is instantaneous. Yeah. Velocity, then, displacement of the objects over time. Miles per hour, kilometers per hour, meters per second, feet per second, yards per second sometimes. So the average velocity, then, is displacement divided by the change in the time, or the time interval that it took. And any practical significances there in terms of speed and velocity? Maybe. I mean, it kind of depends upon what it is. The big thing, though, no matter whether you use speed and velocity, because, well, again, we use those terms interchangeably almost all the time. But again, they don't necessarily mean exactly the same thing. What is going to matter, actually maybe a little bit of stuff that we'll talk about today, is mass and the acceleration of that mass. That's the big part. A baseball that weighs, what's a baseball? 142 to 149 grams right there. Going at 100 mile an hour, that's going to hurt. But I would imagine, I don't know, a bowling ball going that fast hitting you is probably going to hurt maybe a little more. So some of that could be the material that it's made of too. So mass and the acceleration is going to play a big role. Speaking of acceleration, rate of change in the velocity. So the number and direction, and this can be summed up also as a vector. Again, another time interval there. The examples we had, car traveling 20 meters per second, speeds up to 60 meters per second within an 8-second time frame. What is its acceleration? So the final was 60, the initial was 20, and the change in time was 8 seconds. So we had 40 divided by 8, so the actual acceleration was 5 meters per second squared, or 5 meters per second for every second. Then the second one was the jogger. Started running at 10 meters per second, stopped completely in 2 seconds, and her acceleration then was minus 10 seconds, or to minus 10 meters per second. So they stopped within 2 seconds because there was the final velocity was negative, or what was 0, and then minus the 10 meters per second for the initial. So 0 minus 10 gives us the negative 10. And over those 2 seconds, so the final velocity again was negative 5 meters per second squared. Motorcycle traveling north at 55. That's kind of one of those ones that might mess people up. I don't know. Probably didn't mess you up any. Traveling north to go get groceries. 55 meters per second for 11 seconds. The acceleration then. So the initial was 55. The final was 55. The change in time was 11 seconds. We have 0 divided by 11. We got 0. Acceleration is 0. I think this is the new stuff. I think this is where it kind of left off. All right. Okay. Beautiful little chart. Beautiful little chart. All right. So describing the direction of the motion, the change in the motion, and then the acceleration that is happening. We've got positive, negative, and then 0 is basically there's no change. All right, so this is where we have to get into a mindset of what direction we're going to be picking for positive and then negative. In this case, if you're facing this figure, the person that is going to your right is going to be going in a positive direction, which you can actually look at this chart and go and separate these into 2 different charts right here. So this would be the separation. So this is essentially the positive direction in terms of their direction of motion, their actual motion that they're moving towards. So we've got the positive direction and then the negative direction then on the bottom. The things that will change, however, are going to be the actual change in the motion, which is speeding up or slowing down, and what the acceleration is doing. So the top one, again, moving in a positive direction, their motion is moving forward. They're actually speeding up. So their change in motion is positive, and their acceleration is also positive. It is increasing as they're starting to run faster and faster. Now let's say they get up to a certain speed and they're happy with that, and then they remain at a constant velocity. So we have a 0 change in motion. Their velocity is the same, and their acceleration then is 0. They're not increasing speed, they're not decreasing speed, they're maintaining it. So just like the example that we just had right there. So it's the same. So there's no acceleration happening. Now, once somebody starts to slow down, then, or potentially stop, still moving in a positive direction, now their change in motion, even though they're moving forward, their change in motion is starting to move backward. And the acceleration is moving in a negative direction. The acceleration is moving that way in what we are perceiving as the negative direction. Moving to the bottom, where the individual is now moving to the left, where their direction of motion is negative. So their change in motion isn't any different than what was seen up at the top. As they are pushing themselves forward, their change in motion is going to be positive. So they're speeding up. They're at a constant velocity if they get to a speed that is sufficient for them that they need to get to. So no change there. And even when they are starting to slow down, their motion is in a negative direction. It's negative. They're slowing down. The big change here, however, is what the acceleration is doing. Still moving in a negative direction. Their change in motion is negative. But now their acceleration is moving that way, towards what we perceive as the positive. They are essentially decelerating, or there's some other force that's causing them to slow down, that's pushing them into a pushing in a positive direction. Confused yet? Everybody? No? Is everyone kind of okay with this concept? Maybe. Okay. Good. Another thing we can actually do with this, and we'll see it here actually today, we can take one of these halves of this figure and actually turn it 90 degrees, and then we got acceleration or deceleration upward or downward. And it's the same principle. All right, we'll move on. Speaking of upward and downward, projectiles. There's a lot of sports that have some type of projectile. And those projectiles don't need to be implements, they can be the body itself. One that comes to mind would maybe be a long jump, triple jump, high jump, pole vault. So it's a body that is in free fall. Even if you just threw the ball and it's going upward, it's still basically a free fall because you have a couple forces that are acting upon it, which makes it a projectile. Nothing else is touching it. You're not touching it. You got gravity and air resistance are the only two other forces that are being applied to it. And with any projectile, we're going to have a vertical component as well as a horizontal component. The vertical component is going to be influenced by the force of gravity pushing down, 9.81 meters per second squared. The horizontal is not going to be influenced by gravity. That's going to be maybe angle of attack, the angle that it was released, possibly a little bit of wind in that case. There, you just throw a ball. always going to have any point that you pick on this parabola, you're going to have a horizontal component moving in that direction. Or it could have maybe been thrown from that side and moving this side. But we throw it to your right. But also, even as soon as you let go of it, there is going to be a downward force of gravity at all points along the path. And that's going to be constant. Any questions so far? Projectiles? So the effect of gravity, like I said, is constant at that 9.81 meters per second for every second. Acceleration. And as long as there's no external force that's acting upon this object, the pattern of the change in the velocity is going to be symmetrical about the apex. So it's in parabola form. At any point that you look at it, doesn't matter as long as it's consistent and equal on either side of the apex. The change in the vertical velocity is going to be symmetrical of maybe how quickly it is slowing down or how quickly it is speeding up, depending upon which side it is now on. Now, the acceleration is probably going to be in maybe the opposite direction. So instead of it moving upward and then decelerating in a negative direction towards the ground, once it reaches the apex and starts down on the other side, it is now going to be accelerating in the negative direction, but the acceleration is going to be moving it down towards the ground or floor. What goes up must come down, and most of the time it's going to look similar to this. Again, long as there is no other external forces that are acting upon it other than gravity. Wind resistance can affect it. Later in the semester, we'll maybe look at the Magnus effect. That can certainly affect it. Magnus effect, the aerodynamics of the particular object. A golf ball is probably a good one to look at. A baseball to a certain extent. But soccer ball, beach ball, volleyball, wiffle ball, certainly going to have wind resistance greater to that of maybe a baseball. Questions? if you remember the show Mythbusters, which is kind of a while now, I guess, they've been off the air for a while, they actually did an experiment that tried to prove this. Now, we know it's proven just by simple physics, but they actually used it with a pistol. They were put a handgun in a vise that was exactly parallel with the ground, and they also had a device to drop the bullet at the same time another bullet was being fired from the gun. And the principle is, if there's a projectile that is shot or thrown or kicked right beside one that is dropped at the same exact time, they will both hit the ground at the same time. Just the one that is projected forward will go through at least half of a flight. It won't be projected upward where you get this nice parabola, the curved path down to Earth, but it's going to start moving downward towards Earth immediately, just by the force of gravity. The same thing is going to happen with the one that is dropped. And the reason is because both of them are affected by gravity only. Most of the time. The one that is projected forward, however, depending upon what the device is, and I mentioned the Magnus effect, which is changing the currents, the wind currents across the object, that could actually affect the acceleration or deceleration and path of the object. All things being equal, and there's no weird wind resistance and curves being put on this object, both of them should hit the ground at the same exact time. There's also been experiments done with arrows fired out of bows. You drop the object, you shoot the arrow, they should hit the ground at the same exact time. It's just the one arrow is probably going to land, 100 yards or 75 yards away, and the other one's going to land at your feet. So, and gravity is the only thing affecting it then, the downward velocities. Flight path and trajectory, the projection angle compared to the horizontal, and relationship to the ground, as well as the initial velocity of the projectile. So how quickly you have projected that object forward. This is what's influencing the flight path, and also how far this object can possibly go. There's a certain point in terms of the relationship between the ground, certain angle, that provides us a happy medium. Good height, but not too high. Don't know what that angle is approximately. Gives us the furthest distance we can throw an object.
45.
Yeah, 45 degrees. 45 degrees. Another factor in this that isn't necessarily mentioned is that the height of the object that is being released. Taller people have an advantage when they're throwing implements. They're higher off the ground, even if both people are throwing at 45 degrees. The person that is taller, they're still higher off the ground. So they're going to have a little bit more of an advantage. Now they can equal that out by the shorter person applying more force to the object, because that goes back to the initial velocity portion of this. In fact, you'll see it quite often in the field sports, in the shot put and discus. The really good shot put and discus throwers, not only are they just bigger people overall, they tend to be taller as well. They have just an advantage, especially in the shot put where it's not necessarily like the discus where it's maybe a couple hundred feet that you're throwing. They're throwing 45, 50, 60 feet. So every inch or half inch makes a huge difference. And that extra foot that they have over someone else is a little bit shorter is going to make a huge difference to them. Yeah, not to say that short people can't be world-class shot putters or discus throwers, but and that was it for any questions? All right, let's start chapter 3. Take a breather, decompress. Linear kinetics, explaining causes of linear motion. Today we are going to be talking about one of my favorite people, Newton. Why he's my favorite? He should have been a politician. All he needed was 3 laws. That's all we needed. That's all we had with him. Okay, let's move on. Let's look at his 3 laws. Newton's laws of motion. Probably heard these before. We'll try to bring them in conjunction with human movement, athletics. So this first law of inertia. There's a few different interpretations of this. They all mean the same thing, obviously. Every body continues in a state of rest or of uniform motion in a straight line, unless there is something else causing it to change its direction, acceleration. So no external force acts on an object. There is no movement if it wasn't moving. If it was already moving, it's going to continue to move at a constant speed. So this is the one that is summed up a lot of times by saying body in motion stays in motion, body at rest stays at rest. Again, but if there was an external force acting upon it, then something will change about it. Everybody seems quiet today. Everyone's tired. Maybe a little bit. It's the second week lull, I think. Take a breather. Law of inertia. Questions? All right. There's a few different ways that this can be reworded. And you can pick the one that maybe sounds a little simpler to you. And those are, number one, if an object is at rest and the net external force acts on it is 0, the object is going to remain at rest. If an object is in motion and the net external force is acting on it is 0, the object must continue moving at a constant velocity in a straight line. If an object in motion, constant velocity in a straight line, the net external force acting on it is 0. So there you go. Very strange depiction of a dumbbell, but dumbbell nonetheless. The reactionary force is U holding it upward, and then the weight of the actual dumbbell itself then is the weight pressing down on your hand. If you're just holding it there, and say it's a 10-pound dumbbell, the reactionary force that you're applying to it is 10 pounds. If that dumbbell happens to be moving, if you're looking at somebody who is actually lifting dumbbell or barbell, and you can measure the velocity. In fact, we actually have devices that can measure this pretty simply. Actually, they're called Tendo units. Basically hook a clip either to a dumbbell or barbell, and it has a cable that's attached to it, and this device that can actually measure the velocity in pretty precise time frames too. But you can measure it, and as long as it's constant, then the reactionary force is 0. So you're basically equaling out how much the dumbbell weighs and how much force you are applying to it. And this is if it's already moving. This is where we get into maybe some confusion when we get into one of the other laws. We'll get to it sometime, whenever that is. All right, questions so far? Newton's laws, first law. All right, conservation of momentum. So linear momentum. So product of the object's mass as well as its linear velocity. So the faster the object is moves, more momentum it has. Also, the larger the object's mass, the more momentum it has. So increasing one or both of them increases the linear momentum. Represented in L, capital L. For most of these equations, this is something I forgot to point out. For most of these equations, we're not going to have actual calculations on the quizzes, maybe on assignments, but most of the calculations that we may have on quizzes, I will let you know kind of which ones you might need to practice. So, the big reason why the equations are here is so that you can see the different parts and see how increasing one or decreasing it one is going to cause a change in the total. So in this case, the linear momentum. So when you look at the total momentum of the system, of the objects, if it's constant, if the net external force is going to be 0. So again, related to objects in motion, stay in motion, not changing the momentum in this case. If the momentum changed, the linear momentum changed, there is some other external force acting on it, such as if the velocity changed, that means there's an external force changing the velocity. If the mass changed, that means there's an external force causing additional weight somehow. So then the external force is not 0 anymore. There's something else that's happening. In most athletics, most sports, we have a constant mass most of the time. There are times where people are tackling other people or people jumping on other people. There's not a lot of sports where we're adding weight as we're running or moving. Maybe a little bit. It might not be substantial. Baseball, football, basketball, but even basketball, at times you're not going to have it actually in your hand. So we shouldn't necessarily be changing, and even the implements, they shouldn't be changing as they're flying through the air. They should remain constant mass. Question? Second law, F equals ma. That's pretty much the simplest explanation of law number 2. So law of acceleration, the net external force is exerted on an object. The object will accelerate in that particular direction of the net external force. And the acceleration is inversely proportional to its mass. The reason is because if you take F equals ma and you algebraically change it around, acceleration 1. Force divided by the mass equals the acceleration. So there's the inverse proportion that we just discussed. So if the force remains the same, one of them have to increase, decrease, or both of them have to increase, one decreases. If mass decreases, acceleration must increase. If mass increases, acceleration decreases. To remain the same amount of force that's being applied. So Newton's second law is a cause and effect relationship. So it is describing what's happening when something changes, possibly even describing directional forces, as long as you have a vector that's describing them. I don't know. So we can look at this too as gravity. It's the same concept. In fact, it's basically the same equation. The force would be the weight and mass is the same in both equations. But the acceleration, we just have a different name for it when we look at weight equation. It's gravity instead of just acceleration. But gravity is acceleration towards a central body. But gravity is also a constant velocity. 9.81 meters per second squared. So anytime an object is starting, stopping, speed up, slowing down, changing direction in any direction, as long as it is not linear anymore, there is, again, some external force acting upon it. Again, cause and effect relationship. And it can be negative, it can be positive. sounds good. What the hell does it mean? It's kind of the point. Let's look at something maybe a little bit more practical. All right, so let's just say we're standing in an elevator. So initially, the only forces that are acting on us then are gravity and the force of the floor that's pressing up on us. So the vertical forces, one pressing up and one pulling us downward. There we got our nice weird looking straight body. And we can easily calculate this out by the calculation below. The net external force is the total. In the vertical direction, we got mass, which is us, the vertical acceleration, the weight, and then the reactionary force exerted by the feet on the elevator. Or by the elevator, excuse me. So pressing upward on us to keep us stationary, hopefully. Hopefully it's keeping us at the same resting position. Then we would have a bad time if we did not. If the reaction force, which is the R in this case, is larger than your weight, you're going to feel a little heavier. And that force is acting upward, and there's an upward acceleration. So we've all probably experienced an elevator. Anyone not been in an elevator before? Okay, good. So you feel this. As soon as the elevator starts moving upward, you can feel it. You feel a little bit heavier. You can feel the weight, the reactionary force is pressing up on your feet. So you're speeding upward in an upward direction. At least at first. At least at first. You start to feel it. If the reactionary force is equal to your weight, you're going to feel nothing. You don't feel heavier, you don't feel lighter. The net force is 0 in this case, and there is no acceleration. This is what happens when you're actually moving between the floors. Once the elevator starts moving, you feel a little heavier. Once it gets to a constant velocity, then you feel normal. I mean, you can maybe feel some movement. I mean, there might be a little bit of rattling inside of the elevator, but you don't feel any heavier or lighter. You don't feel any additional force pressing upward on you. Once you start to slow down, reactionary force is less than your weight. You're going to start to feel lighter. The elevator starts slowing down. The net force is acting downward. There's a downward acceleration. So you feel a little bit lighter. You might not feel weightless, but you feel lighter. Now, if you could be in an object where you do feel actually weightless, one of those, any type of amusement ride, sometimes will do this to you, where it just drops you. That's essentially what's happening here. The reactionary force comes much less than your body, sometimes even 0, and then you basically just fall to earth, and then there you go. So it's the same concept that we applied to this figure. In this case, we can turn it turn it 90 degrees, and we have the 3 elevator examples in this case. So the first one here, as we are moving, whoa, what is that? Moving upward or starting to move the elevator. And the next one is we are moving between the floors. So we're at a constant velocity, there's no acceleration. And then we are starting to slow down as we get to the floor that we are wanting to get to. We're still moving in a positive direction, upward. Constant velocity, though, is now negative. We're slowing down, and our acceleration is moving downward in a negative direction. What we would describe as negative, because normally we think is going up is positive and going down is negative. But I guess if you were upside down, then maybe it would make a difference. Or if you're in the South Pole or in the Southern Hemisphere, it might change. Maybe not. Maybe. Okay, let's go. All right, going back to that 10-pound dumbbell. Newton's second law. So lifting the 10-pound dumbbell, the external forces on this are going to be the pull of gravity acting downward. And then the reactionary force of your hand pressing upward on the dumbbell. The net force of these is the difference between them. So the example with the elevator is akin to the example with, is an example of the dumbbell. So your hand is essentially the elevator. Your arm, I guess, is the elevator. So as you start to lift that dumbbell, you actually must accelerate the dumbbell and put more force on it than the weight, the force of gravity times the mass of the dumbbell pressing down to get it to move. Just to start it, to change its acceleration. So in this case, if the dumbbell could talk, which I know some dumbbells that could talk. Okay. Joke for the day. If the dumbbell could talk, it would say, I felt a little heavier. I could feel the excess force pressing up on me. Now, once you get the dumbbell moving, how much force do you need to apply to it? Equal to, greater than, or less than the amount of weight of the dumbbell? What do you think? Kind of goes back to law number 1. Basically, equal to keep it moving at a constant velocity. We're not accelerating, we're not decelerating, we're just keeping it the same speed and or velocity. So to continue to move it requires only the net force to equal 10. Wait a minute. How? How does that? So you need a little bit more to get it to go, but to keep it going, you just need equal to. The reason is, and let's go back to one of the first slides where we looked at the interpretations of the first law. Object in motion at a constant velocity in a straight line, the net external force on it must be 0. If there's any external force applying additional acceleration to it, then it's going to change direction, accelerate. You can do that, but to just get it moving in a constant velocity, you do not need to put any more force upon it. That's why. But to get it to move, then you need a little bit additional force than the actual weight of the object. I mean, you don't need like 30 pounds of force to move it, depending on how fast you want to continue to move it. So as the dumbbell then is moving in, I guess, from your starting position throughout the range of motion to the ending portion to where basically the top of maybe a barbell or dumbbell curl, if the weight could talk, it would say, I feel normal. I feel like a normal 10-pound dumbbell. And then once we start getting to the end of that particular motion, particular motion, as you complete the lift, you're going to start to slow the weight down. And by slowing that down, you are going to be applying the total net force is going to be downward, and it's going to be less than 10 pounds. So the dumbbell in this case would feel like they maybe are a little bit lighter than 10 pounds. So you could actually calculate this out. And we could also look at it representatively in the chart or the graph, whatever table that we looked at with the stick figure. So in this case, this one down here that one would be as we get it to move. This one, the center one, would be as we are moving it throughout the range of motion between the starting and stopping points. And then in the last one, we are slowing it down and possibly coming to a stop. Then once we stop lifting the weight, either to the top or the bottom, then we go back to law number 1. There's no external force causing it to accelerate. So must be equal reactionary forces, net external forces. Questions? Concerns? Nothing from the online gallery yet? You guys are still awake? Good. There's a concept, we'll revert back here a little bit to friction. So accelerating something vertically actually requires a little bit more force than horizontally. A simplistic example here would be a ball. Part of that is because it's round, but doesn't take nearly as much force to accelerate it vertically as it does pushing or pulling it horizontally. The biggest reason is because under normal conditions, and sometimes this actually can be varied depending upon the surface that you're pushing something across or the frictional coefficient of the actual object. But most of the time, frictional forces aren't as great as the gravitational forces pressing down on that particular mass. Again, not to say that there aren't times where it's more difficult. If that ball had some type of super glue on it on the floor, then it might be a little bit tougher to push it. But to roll it, maybe. Which also the shape of the object comes into play too, I guess. That's how some of the ancient people, I believe, built a lot of the structures. They just rolled them on logs or wheels, round objects. I think we'll end there for today. I think it'll be good. We'll finish this chapter up with a little bit of momentum stuff, as well as Newton's third law.